Okay, so here is probably the most, well, one of the two most important definitions in this section. So a zero divisor in a ring R is a non-zero element Z in R such that there exists a non-zero element X in R, oops, with either Zx is 0 or Xz is 0. One of the two. It doesn't have to be both. So let me just point out, not necessarily both. At least one, though. So let's revisit the examples that we saw in the last video with this idea of zero divisors. So in these first two examples, what we would say here is we would say that 2 is a zero divisor, as 2 times 2 is 0, and that's the non-zero element. So this is our z. We could think about that as our x, or the other one as our x. And we would say here that a is a zero divisor as well, because a is non-zero, a times something non-zero gives us 0, so a must be a zero divisor. And then with these examples, we argued actually that there are no zero divisors. So z and z adjoin x have no zero divisors. So if a product was 0, one of the terms had to have been 0, or equivalently, if we product together two non-zero things, we argued that that you had to always get something non-zero. Great. So this is our definition of zero divisor. Those are a couple examples. And let me point out something that we learned actually from when we were looking at units and associates in Z. So just maybe we'll do one more example. Well, we did this in class, but I might remind you on a homework or something like that, that the zero divisors in Z mod M are precisely the A's here, such that the GCD of a representative and M is bigger than 1. Because those are precisely the terms that have something in common with M. And once you have something in common with M, you can product something else non-zero with it, namely the rest of the stuff that's in M, to be 1. So for example, to be 0. For example, as a hint as to how you might go about thinking about this, let's consider Z mod 10. And let's look at something that has something in common with Z mod 10. Let's take some 4 bar in Z mod 10. Then the GCD of 4 and 10 is of course 2. So they share 2 in common. And if we look at sort of the quotient, so 10 is 5 times 2, for example. So we look at the quotient Q when we divide 10 by the GCD. That will tell us how to come up with the other element to get 0. So we started with 4, we looked at the GCD, we divided 10 by the GCD. 4 times 5, we got 5, and I claim 4 times 5 is 0. Well, 4 times 5 is, both of these are non-zero in Z mod 10, and 4 times 5 is 20, which is certainly 0. Okay. So whenever you have something in common with the modulus, you can do a process similar to this, and I think I will actually assign this as a homework problem. But it goes exactly like this example. Nothing's really that different. So the zero divisors in Z mod M are precisely these. And let me also note one thing here. If M is prime, then Well, there are no non-zero elements that have this property. There does not exist. A bar is in Z mod M such that the GCD of A and M is bigger than 1, as they're always equal to 1. Non-zero, I should say. And this is going to be a shadow of a fact that we're going to prove later. The collection of zero divisors and the collection of units, which if M is prime, every non-zero element is a unit. The collection of these different types of elements are disjoint. They don't share anything in common. So in a sense, they're kind of opposites of each other.